we're going to talk about tension here now, we have to ignore a few things. When we talk about tension, we ignore. We're going to ignore the mass of the rope, which is not true. Ropes are not massless, and yet, as far as we're concerned, they're going to be today. And, well, everywhere I've ever looked at tension, that's not true. Almost everywhere I've ever looked at tension, we have to assume the rope is massless. I had not seen the appropriate, mass included description of tension until I was 3/4 of the way through my master's degree. That's how long you ignore this stuff for. We can talk about it without it, but it requires a certain level of mathematics that we just don't have, and I didn't have for a long time, to even consider talking about the mass of the rope. So we're going to ignore it. As far as we're concerned, we're also going to ignore the elasticity in the rope. Let's ignore springs. We know everything is slightly elastic. We're going to toss that out. Ropes have no mass. Ropes are inelastic. And for a large portion of this, we are going to ignore friction. In pulleys. Because when we look at tension, it also makes sense for us to look at the pulley. So again, suspending our belief about the world in a few ways. We know ropes actually have mass. If I throw a big enough rope on you, you will collapse under its mass. We know ropes have some elasticity. There is some give to these things. And I mean, nothing is totally frictionless, and yet we're going to treat it that way. So, when we talk about tension, tension occurs within a material that is being pulled on. Now, the kinds of materials we typically consider are things like string, rope, chain, cables, etc. Those kinds of things are the kinds of things we typically consider as having tension. There are other things that you could think of having tension. We talked about your skin. Skin's another one that has elasticity and it has tension. But these are typically, the simple examples we're going to look at, this is typically what you're talking about. Tension is an internal force that acts at all points along a rope or string or chain or whatever. It acts at every single point, so infinitely many places throughout the chain, and it acts in both directions. Now, obviously, we're not going to look at every single point throughout a rope. That would be a lot of work to do. But we're going to generalize these pieces. We're looking at specifically the ends of each of these ropes, strings, chains, whatever. So let's consider this. We've got a cart. We got two carts attached by a rope being pulled along a flat surface. Because they're on wheels, they are rolling, not sliding. Because they're rolling, not sliding, friction is negligible, means we can ignore it. If the mass 1, this is the one that's labeled M1, if M1 is pulled to the right by a force of 40 newtons, we want to find the acceleration of the system of carts. So let's draw some free body diagrams here. The only way to analyze these things, and for everything we look at in this chapter, we need to draw some free body diagrams. So, what forces are acting here? Gravity's acting on both of them. You bet. From the center of each cart, we have gravity acting straight down. We could figure out what that value is. Fg is going to be mg. So the mass of cart 2 is 6 times 9.8. This guy's going to be 4 times 9.8. Whatever those values are. At this point, it doesn't really matter. What other forces are acting on these two carts? Normal forces. Assuming that, I mean, we're not told, but assuming that the ground is level, if I can draw level ground. Let's assume that the ground that I've just drawn is level. Normal force is acting which way? Not always. Don't think about it as acting opposite to gravity. In this situation, that is true. In general, normal force acts which way? Perpendicular. To what? To the surface. That just so happens to be that gravity is also perpendicular to the surface. So yes, Vine, in this particular case, Fn and Fg are opposites. And if they are opposites, they're also equal. But for the sake of what's coming, we're going to start putting things on inclines here in a little bit. Don't think of it. Try it as much as possible to avoid saying that Fn and Fg are opposites. Sometimes that's true, sometimes it's not. And I'm going to label these because these Fg's are not the same. I'm going to call this Fg2. I'm going to call this Fg1 because we labeled that mass 1. So I'm going to call this Fn2 and I'll call this Fn1. Okay, what other forces are acting on these two carts? We're told that there is a 40 Newton force to the right on M1. So we can draw that guy in there. We'll call it an applied force. F applied equals 40 newtons. It's acting to the right on that guy there. And we've got a rope attaching these two things together. So this is where, in these diagrams, wherever there's a rope, this is where tension gets introduced. This cart is getting pulled to the right. How does this cart move? It's also going to get pulled to the right. But if we're going to label the forces here, if it's getting pulled by this one, what's causing it to move? Because you didn't grab this, you grabbed this. How is mass 2 experiencing a force if you didn't touch it? Yeah. The rope, yeah. The tension in the rope is what's causing this guy to follow this guy. So we can label that as part of our free body diagram. This mass is experiencing tension to the right. That's what causes this mass to move. If this thing is attached to this thing by this rope, what force needs to be labeled here? Tension. Which way? Backwards, yeah. So tension acts both ways along a rope, and everywhere within the rope, as long as it is the same rope, the tension is equal. So these two tensions, even though this one's on M2 and this one's on M1, because this is the same rope all the way through, these two tensions are actually equal. This block isn't going to move as quickly to the right as if this, like if the rope wasn't here. And if this rope wasn't here, this guy wouldn't move to the right at all. So we have to take into account in our free body diagram, we have to take into account the fact that there are, that these tensions do exist in here. They're equal, they're opposite, and they act everywhere along that rope. So now there's a minor discussion we have to, well, all of this is discussion. If I want to talk about the acceleration of the carts, what can you tell me without doing any calculation, just in your experience of the world, what can you tell me about how these two carts are going to accelerate due to being pulled to the right on this guy? Just in general terms, how are those two carts going to accelerate? Yeah. They're both going to accelerate to the right. Yeah. What else can you tell me about those accelerations to the right? You don't think it would be the same? Now you do think it would be the same. That's the opposite of what you said before. So what you're suggesting is because this one is here, this one is going to accelerate slower than if it was just this. Makes sense. But they are hooked up, so the overall acceleration is going to be lower. What can you tell me about the accelerations as they were this acceleration versus this acceleration? You said it before, I want you to say it again, but I want you to commit to an answer. How are these two accelerations, because this thing's attached, going to relate to each other? They're going to be the same. It doesn't make sense for one to accelerate slower than the other, mostly because we're ignoring the elasticity here. So when we're going to go through and calculate the acceleration of the carts, what we're going to, there's two ways you can handle these kinds of questions. I think conceptually, the way I like to think about how these questions are handled is the carts accelerate as a system. They accelerate together. Because they're attached, they accelerate together. The accelerate excuse me, the accelerations of the two are going to be the same. So we treat them as one system. They accelerate together. So now when we're going to go through and try and calculate the acceleration for this system, we're going to treat them as if they're one object. So for everything in this unit, dynamics unit, everything starts here with Newton's second law, F net equals ma. Now, if you recall, F net is the sum of all of the forces in the same direction as whatever the acceleration is. So these two things are presumably going to accelerate to the right. They're being dragged to the right. They're not going to accelerate up into the sky or down into the ground. So when we consider F net, the only forces we need to consider are the ones that are acting parallel to or with the direction of acceleration. There's one thing we still need to add to this diagram. For the sake of the math that's about to come, we need to pick a direction to be positive. So what direction would make the most sense to declare to be positive in this situation? To the right. It's being pulled to the right. Let's call that direction positive. Okay, so then starting at the right and working our way left, because to the right is positive, let's figure out what this F net is. F net is the sum of all of the forces acting in that direction. So starting over here, FA is going to be positive because we said to the right was positive. So we're going to have FA. As we keep going, we hit this tension force right here. This tension's acting to the left. So we're going to subtract that tension. We keep going left, we hit this tension. This tension's acting to the right. So we're going to add in that tension. These two tensions are the same because they're acting within the same rope. And now we come to MA. Because these things are accelerating as a system, we're treating them as one system. What would make sense to do with the mass here then? Combine them. So then the mass for the acceleration of the system is the total mass of the system, m1 plus m2. And to that we multiply A. We're looking for the acceleration here. So now we can actually go through and plug in some of these values. We know that this acceleration, this applied force, FA, is 40. Negative tension plus tension is going to cancel. Because it's acting in both directions, it's not going to have an impact on our acceleration. So these are going to add together, give us 0. This is going to equal, well, M1 and M2, we're going to add those together. M1 was 4, M2 was 6 times A. So 40 equals 4 plus 6 times A. BEDMAS says I need to add the 4 and the 6 together. So then the acceleration is going to equal what? 40 equals 10A. A equals 4 meters per second squared. And that acceleration is going to be the same for both objects. So the note here for tension, because, well, the tension in this particular example cancels out because they are equal and opposite. Should have made that box bigger. So we found the acceleration of the system. It means that individually, these two carts will accelerate at 4 meters per second squared. The next portion to all of these tension questions is actually to now go ahead and figure out what the tension is. We found the acceleration together, we treated them as one system, and now we want to find the tension in the string. When we treated them as one system, the tensions canceled out because in the entirety of the system, we had a tension acting to the right and a tension acting to the left. When we treat it as one big object, those two are going to cancel. So, anyone want to take a guess as how we're going to go about finding our tension then? Yeah, we're going to isolate the carts individually. Because we know that this acceleration is the same for both, to find this tension now, we just need to isolate for a cart that is experiencing that tension. In this case, both of them are experiencing that tension. You can pick whichever one makes the most sense and focus just on that cart. Given the free body diagram, which of those two carts is going to be the easiest to use? Alina's suggesting M1 here today. Why cart 1? Okay, does anyone have another opinion? But why cart 1 might not be the best choice? At this point where we are kind of, sorry? I mean, tension's negative, part of it. There's also, when we, so okay, let's isolate, we'll start with cart 1. You both want cart 1, no one else has given an opinion, so let's isolate cart 1. When you're looking for the tensions, isolate a cart, whichever one you want, experiencing that tension. So you guys chose cart 1, okay? We're going to start this portion the exact same way we started the previous one. We're going to look at F net equals MA just now for cart 1. What's our F net expression going to be for cart 1? Yeah, we're going to have an FA minus FT equals MA. And now I can start plugging in some of these values. We know FA is 40 minus FT is what we're looking for. The mass now, because we've isolated cart 1, the mass of cart 1 is 4, and we found the acceleration to be 4 as well. So I can go ahead and solve this thing. I'm going to add FT to both sides, and I'm going to subtract over this 16. So we're going to get 40 minus 16 equals FT. So the tension in that string is going to be 24 newtons. Questions about what I've just done? Okay, well, just for fun, let's go look at the other cart. Does cart 2 experience that same tension force? Yes. The answer I'm looking for all of you on this Friday afternoon last block is, in fact, it does. This rope is attached both to cart 1 and cart 2. This tension is felt by both cart 1 and cart 2. The only difference here is that on cart 2, what's significant about FT? Yeah, it's dragging it forward. So this one, in this case, FT is going to be positive. And are there any other forces on cart 2? No. So that might be, that's the one kind of really great reason to have picked cart 2 over cart 1. In cart 2, if you look at how this equation is going to go, if F net equals MA, the only force acting to cause this thing to move is FT. So this thing's just going to become FT equals MA. So FT is going to equal 6 times the acceleration of the system. 6 times 4 is 24. It's not like it's a lot easier, but cart 2, because the tension force is the only force acting in the direction of motion, cart 2 would have been the simpler one to pick. But again, we've done both now. It doesn't matter which one we pick. Because that tension's being experienced by both carts, we can use either cart and we're going to get the same result. Whichever one you isolate, the tension in that rope is 24 newtons. So, since it cancels out of the total F net equation, we only consider the forces acting on one cart. And since tension acts on both masses equally, we can use either cart. Comments, questions, concerns about what I've just done? Okay. Hearing nothing, let's make this more interesting. Let's combine it with some stuff that we've looked at already. What about friction? Now, I did say before that we were going to ignore friction in pulleys, but we don't have any pulleys yet. That's on the next page. Let's look at friction here. Imagine that for a second, the wheels fall off of the second cart, and the rest of it drags along the ground with a coefficient of friction of 0.32. What's going to happen to the tension? What do you think is going to happen to the tension? You take the wheels off this cart, and you continue to drag this system to the right. So the friction that wasn't there before is there now. That's increased. So the acceleration is going to be slower. What's going to happen to the what do you expect to happen to the tension? It's going to? Why would it decrease? Why would it increase? This one's experiencing the same force to the right, you bet. This thing is now experiencing an additional force back. So the tension should increase. This thing's getting harder to pull. This force hasn't changed. So let's take a look at it. Let's actually analyze the problem numerically. So here's what we've got. We've got some ground. We still have a cart on wheels. It's still being pulled to the right with a 40 Newton force. But now, cart 2 has no wheels. It's being dragged along the ground. So let's finish the free body diagram for this thing. They both still have gravity acting down. FG2, FG1. They both still have a normal force acting up. FN2, FN1. Because there's a rope between the two objects, they're still both experiencing a tension. This one's experiencing a tension to the left. This one's experiencing a tension to the right. They are the same tension, so I don't need to label them because they're equal. Don't need to differentiate between the two. But now, because this guy has no wheels, it's being dragged along the ground, it has a friction force acting to the left. There's a friction force acting left. Because the whole system's trying to move to the right. We're going to still call to the right positive. But now we've got more to deal with. Up here, when I was including the free body diagrams, I put values in for M and G on FG, but we didn't actually need them. Down here, how are we going to find friction? Friction is equal to what? Mu Fn. Friction is dependent on the normal force experienced by our object, and in this case, Vian, Fn equals what? It just so happens to equal. Yep. Equal to and opposite the force of gravity. So now in our free body diagram, it actually makes a lot of sense to go ahead and calculate this. We need Fg because it's going to be equal to and opposite Fn, and we need Fn because we've got a friction now. So Fg is going to be 6 times 9.8. The masses of those carts haven't changed, which I did the math for us is 58.8 newtons. This is going to be equal to Fn because 58.8. Because the ground is level, gravity is straight down, normal force is straight up. So we can go ahead and calculate a friction force now. We're told that the coefficient of friction is 0.32. That's the value for mu. So 0.32 times Fn, we know it to be 58.8. So how much friction is acting? Well, you do this math. I got the value for us. It's going to be 18.816 newtons. So now we've got a free body diagram with all of the information we need. We've got an applied force to the right, tensions acting left and right, and a friction force acting to the left on the second block. To find the tension between the two objects, we need to find the acceleration of the system first. Here they suggested that this value for the acceleration should be smaller. Let's go back or let's go through now and figure it out. For everything we looked at here, we have to find the acceleration first. Acceleration. Here we go. Everything we do starts with Newton's second law. F net equals ma. What's going to be the expression for the F net now? F net is the sum of the forces in the direction of motion. What forces are acting? Yeah, Lena. You bet. You've got two forces acting to the right, Fa and Ft. You've got two forces acting to the left, Ft and Ff. So this is what your net force expression is going to be. This is going to be equal to m1 plus m2 because they're accelerating as a system. We add their masses together, whole system. And now we can go ahead, plug in some values, and figure out what the acceleration of our system is going to be. Fa is 40. The Ft's are going to cancel. So we're going to get 40 minus Force of friction, we have a value for 18.186.816 equals 10A. You guys are a popular crew today. Lots of you are getting texts. You solve this thing for A. I'll give you the value. You should find that this is 2.1184 meters per second squared. So here they figured that that would be a lower acceleration than before. In the first one, when they both had wheels, the system was accelerating at 4 meters per second squared. Now, when the wheels fall off the second cart and it experiences friction, we have an acceleration of the system of 2.1184 meters per second squared. Here it is, intuition was right. So now let's go ahead and find the tension. It doesn't matter which cart we isolate. I'm hoping I convinced you of that before. Just because now we've got friction here now, doesn't change that. It still doesn't matter which cart we isolate. So to find the tension, which cart do you want to isolate? Cart which? I mean, technically speaking, I labeled them 1 and 2, but you mean the one experiencing this guy? Yeah. Okay, so let us look at cart 2. If we isolate cart 2, our F net equation is going to look like what here, Dave? Sorry, what forces are acting on cart 1 or cart 2 rather? Yeah, it's Ft minus Ff. Fa was acting on this guy. So if you want to use cart 1, it's going to be Fa minus Ft. Using cart 2, it's going to be Ft minus Ff. You bet. Okay, so because you chose cart 2, it's going to be the tension force acting to the right minus the friction force acting to the left equals Ma. And now we can plug all these values in there. We're looking for Ft. We know the friction force is going to be 18.816. We know the mass of this cart is 6. And we know the acceleration of the system is 2.1184. So Ft is going to be 6 times 2.1184 plus 18.816. The acceleration is smaller, but we're adding something now to work against it. The tension, if you do this math, you're going to get 31.5264 newtons. So here today, it was 24, it's now 31. Your intuition was correct. Tension's gone up. And it kind of makes sense. Like if it's harder to move the system, the tension between the two objects is going to be greater on that rope. If we want to use cart 1, we get the exact same value. The only thing that would change would be, well, there are two things that would change. The forces acting on this side and the mass of the cart. If we looked at cart 1, the mass would have been 4, and these forces would have been Fa and Ft. Questions about what I've done there? Okay. For the sake of time, given that it's a Friday, I've only got 20 minutes left. I got 4 more examples I want to do that bring in pulleys. I feel like it would be best for us to forego these examples, push them to Monday, and give you guys some practice with the tension that I've given you with the little time that we've got left. Also given the fact that you guys seem right done with this week. So, I'd like you to flip ahead, a couple pages, find this page, the tension challenge. I want you to look at a bunch of these. I only dealt with forces act like a system acting left, right, but it doesn't actually change anything if you start raising and lowering the system. So there's a few that I'm going to give to you here. Do I want you to have multiple objects? You could do multiple objects. Okay, I lied. Go back one page. I want you to do question 3. And I want you to do question 4 off this page. Ignore the pulley ones for now. We'll come back and deal with those on Monday. Take a look at 3 and 4 there. And I want you to do, on the next page, take a look at 8. I think that's it. No, we'll add one more. 3 and 4 up top. So there's 6 questions there I want you to look at. 5 questions? Question 3, question 4 on the front page, 3 and 4 on this page, and question 8. We'll leave the pulley stuff and the rest of these questions till to Monday. You've got about 18 minutes till the end of the day. Give her. This is tension.